Hello, everyone. My name is Maz Barami from Wolfram Research. Uh, Me and Nick are the main forces behind what we call as Wolfram Quantum Computation Framework, which is practically a packlet, a collection of functions to do quantum computation. Okay, so let's see how we are gonna handle this week. You have already we have provided a collection of notebooks containing everything that you need, and it's a very typical format of all courses. But our presentation, we are gonna do some tweaks, some minor changes. The main reason that we are doing that is basically just to challenge you and trying to trigger your interest and get you engaged more. So again, everything that you need is in those notebooks, but what you see here might be a little bit different from those notebooks. uh, we usually call them flip classrooms format. We give the material to the students, and then when it comes to representation, we do something a little bit different. Okay, let us start with talking about our quantum computation framework. Remember, the Wolfram as a company, especially because of our CEO, Stephen Wolfram, there has been, for any name that you see related to our company, lots of discussions, why that particular name and why not, for example, quantum computing. So let me just be very clear from the very beginning. The main reason that we call it quantum computation is mostly because it's about, doing computation for a discrete finite dimensional Hilbert space. Okay, so it's not only those topics, those computations that we conventionally call as quantum computing. It's everything quantum, and of course, because we have a complete functionalities, everything that you in quantum computing is also included. Okay, you would see there are lots of functions, there are lots of interesting properties that we are going to review. They are very interesting if somebody is doing very abstract quantum computing type of research. Of course, a big portion of functionalities that we are going to discuss are directly related to what we call as quantum computing and etc. But anyhow, so that was just a quick intro about what we are planning to do. uh, I guess you are familiar with this environment. There are some folks who are very well aware, experience in Wolfram language, and also our quantum framework. Any question, you can put it in the chat. People, they would respond to those questions, and if needed, they'll bring to my attention, and I can comment on that too. um, as I told you, this framework, the main forces behind that, me and Nikolai is also here. uh, it's a packlet in our packlet repository. This is the link for that. And if any issue, any question, any comment, any feedback that you may have, just contact us at quantum@wolfram.com. So this is the best way of communication you could have with us. Now let us start with packlet installation. What is the idea of packlet installation? Basically, you are going to add a collection of quantum functions into the building functions that you have in Wolfram Mathematica. So that's the idea of a packlet. There are two ways of installing that. The one that is already deployed, this is the link, literally packlet install Wolfram and quantum framework. But since this is an ongoing project, that and literally me and Nick every day we work on that, do debugging or updating and adding proper functionalities. We recommend you guys to install it using this link, because this is the latest one that basically the most updated one. And if any bug, we take care of that on daily basis. But most of them, they should be almost the same. So I'm just gonna bravely evaluate this cell, which is for the packlet installation. Grinding. Hmm, it should be faster. It depends my internet connection, and the platform that we are using for the representation is taking a big. Huh, what's happening? Hold on a 2nd.
This is some connection issue.
Yeah, I know. That's what I said. Like, it has nothing to do. It's just the platform that we are using for the representation is consuming all of my bandwidths. My laptop is very slow and
Oh, just pretend you installed it with that link because
okay,
you already
let's see.
showed
Like,
it.
do I have all the functionalities? Yeah, okay. So anyhow, like, just install them and let me just show you, like, see what do we have, like, okay, so these are the collection of functions that will be added. By the way, these two links works, like, the error that you see here is just my connection. As I'm representing, it takes like Zoom. It's even worse than Zoom. So anyhow, these are the collection of functions, like, to do any quantum computation. Some of them are designed for something very specific. For example, quantum basis is for quantum basis, quantum channel is for quantum channel, quantum circuit operator, that's the function that we are going to use for circuit design. uh, but some of them, like, are not for a very specific, like, quantum object. For example, when we discuss about quantum distance, so this is basically a function to quantify the measure between two quantum states or quantum entanglement monotons. So, like, this is to measure, the entanglement monotons between two quantum states, quantum entanglement q, like, asking if a quantum state is entangled or separable. So as you can see, some of them are for some particular, objects that has a very specific meaning, but some of them basically they gives you a numerical result, or, like, a true false. Okay, so what I'm gonna do, I'm gonna start with those functions that are basically, returns a very particular object. Okay, so, like, these are your objects that you would do, like, quantum computation. uh we had a sort of, discussion, me and Nick, like, how we should represent our framework historically. Like, it's funny to say historically, because this framework is basically, it was born about 1 year ago. But anyhow, in the past year, whenever we wanted to represent that, that was our workflow. We started with the basics. Like, we would have started by talking about quantum basis, how to define your Hilbert space. Then we would move on, to the quantum state. After quantum state, we would introduce the idea of, like, quantum operator, some transformation. uh, for for your, quantum state. Then we would introduce the idea of, quantum measurement operator to basically work with the measurement. At the very end, we would, comment on quantum circuit operator, when you have a composition of, different operators. uh, by experience, we learned that, like, maybe this is not the best approach, starting from the very first fundamental ideas, and, like, telling people how to do the constructions and etc. That's why, like, recently, very recently, we decided to do a sort of, reverse approach. So what I'm gonna do, I'm gonna start from the very end, quantum circuit operator, because, like, many of you are interested to learn how to deal with the circuit, how to construct your circuit. I'll give you the big picture, like, basically, like, look, this is what we are gonna do, this is how we are gonna, like, set up everything. And then, like, step by step, we are gonna dive in, and we are gonna explain each of those functionalities in much more detail. So at least, like, in this way, you have a bigger picture. So basically, like, we can refer to other functionalities whenever discuss, like, different functionalities. Okay, let us start with the idea of, quantum circuit operator. uh, what is, a quantum circuit? This is the way that we recommend to see a circuit operator. So it's basically a composition of, bunch of quantum operators. When we talk about quantum operators, see them as, like, some transformation happening to quantum states. And quantum states is basically the mathematical tool describing a quantum system. I have seen, in some literature, quantum state, they replace it by quantum data. I do not like that terminology, so I still prefer to call it, like, quantum state. But anyhow, you can also see it as, like, quantum data. So when you have a composition of bunch of transformation on your quantum data, this is what we call as a quantum circuit. Okay, and of course, when we talk about quantum circuit, what is important is, a sort of, a stepwise transformation. So, like, like, you are going to have a collection of operators in a very particular order, and you are interested to get a very particular functionality out of that collection. Okay, so that's the idea of circuit. So circuit is a composition of quantum operators. So fundamentally for us, what is important is quantum operators. Okay, keep that in mind. So quantum circuit, interesting, but behind the scene, it's practically a quantum operator. How we should think about constructing a circuit in our framework. This is the most important, basically, pattern that you have to remember. So you would start with your quantum circuit operator, and you give it a list of operators. So that's one approach. Another approach is that we have a collection of named circuits. Practically, these named circuits, they are a composition of bunch of operation for a very particular goal. For example, you want to do quantum search algorithm using Grover algorithm. So instead of constructing everything manually as a collection of operators, if you can, I know sometimes it's a headache to construct uh, to understand what is the true oracle for this very particular situation. But anyhow, behind the scene, you can do everything automatically using our name circuits. I will comment on each case in more detail. And then if you are interested to see what is the action of your circuit operator on a corresponding register state means all of your quantum states are in the ground zero state. That's basically the syntax that you have to use, basically. So here you can also put your quantum state. If if any state other than register state, you can add your quantum state. But most of the time it's going to be a register state, because conventionally, if any transformation on the register state, researchers, they include it as part of circuit operator. Anyhow, so let's go through some examples. Look at the very first uh, example that we have. Okay, so let's look at the first circuit. So we have quantum circuit operator, and the input is x. So basically, it's a circuit with Pauli matrix x. There are two ways. The what you see here is a traditional form, basically the circuit diagram. And the previous case, it shows you an object. So this is the object that you see. Each object, it has a summary box. If you click on that plus sign, you see it gives you some more information, how many gates, what is the dimension, what is the order, and etc. So uh, some people, they prefer the diagram because it gives you a better visualization. Some people, they prefer that summary box. Let's look at the second example. So now what we are giving as an input is a collection of the Pauli operators. So we are saying x, y, z. So automatically behind the scene, our framework understands it as Pauli x on the first system, Pauli y on the second system, and Pauli z on the third system. Okay, now let's say that you only have one gate, and this time, instead of that gate acting on the first qubit, you want to say it acts on the second qubit. So what we need to do is just we're defining as a rule, and that too later on we are going to explain. And this is the order of your operator. So literally that code means Pauli x acts on the second qubit. And as you can see on the first one, when there is nothing, it means practical identity. And of course, we can have a collection, a collection in a very particular order, which is basically the next example. So before evaluating, let us just try to understand what's happening there. So what we are doing there is Pauli x on the second qubit, H is for Hadamard. As you can see, Hadamard, it has no no other arguments. So automatically, whenever nothing is given for the order, we would interpret it as one. So you can add one, or you can just remove that. It doesn't change anything. So as far as the order is one, by default, we are going to set it as one. And when you evaluate that, you would see, so X on the second one, Hadamard on the first one, and then Z also on the second one. And look at the order, because the order is also very important. So the circuit, diagram, we read it from left to right. So it means the Pauli X first, then Pauli Z. So the time order is from left to right, in the circuit diagram. Here we are just using like, the operators that are separable. So like, when we are applying that Hadamard, it doesn't, it's not important. Of course, there are many operators that simultaneously acting on more than one system. For example, C naught is a control gate that basically has a control qubit, target qubit. The example that you see here, as you can see, no input is given other than just the name of that operator. So it means automatically behind the scene by default, we are going to set control as the first, target as the second one. Okay, so that's basically the situation that we have. And like, the notation that we are using is the conventional notation. Now you can change that. You can say that, look, I would like a C naught. This time C naught, the second one will be your control, and the first one will be the target. Okay, so whenever we have the solid, circle is for control one qubit. Um, Now, behind the scene, whenever we talk about quantum circuit operator, you remember I told you a composition of operator, composition of gates. That's what we call them. How we can see that operator? So if you just ask for the property operator, this is the collection of operators that we see. So the first one is Pauli X. It's a quantum operator Pauli X acting on the second qubit. Then we have Hadamard. As you can see, each one has a summary box, and inside the summary box you can see like all the information that you need. The second one, you see it's the Hadamard. There is no argument, so automatically the order is on the first one, and the last one, Pauli Z, it acts on the second qubit. As you can see, the summary box, it contains some other interesting information. For example, if it's Hermitian, if it's unitary, etc. So you can get it like directly, or you can get it like manually, like through some operations. By the way, each of those objects, they also have traditional form. For example, Nick showed the traditional form of one of them. So you see like all of them. Actually, this is a traditional form of all of them. You see the top one is uh, Pauli X, the second one is Hadamard, and the last one is Z operator. Okay, so again, like, oh, by the way, the shorthand for traditional form on Mac is Command Shift T, or you can literally at the end just type traditional form. So both ways works. So that's how you can see the traditional forms. Uh, so here you see that circuit as a, so the other one, N standard form. And then you can easily switch between the two, so you can see them as the object with the summary box or this traditional form. I don't know which format our users prefer. Like I know some users, they like the traditional form, some other users, they are good with the objects. Remember, like for simple operators, yes, traditional form, like I know most of you understand the traditional form, like better than the summary box. But as you increase the dimension or the size of your gates, the traditional form will not be very helpful. Okay, so like I don't know, just let's go one example. A random unitary, yep, in dimension 5, and look, this is basically the traditional form. Uh, and by the way, like this is the representation in the usual bracket notation. You can ask for other properties. We will discuss about that very soon. Now, another way of looking at the circuit, instead of like a collection of operators and their application one by one, you can ask for one single operator representing the whole quantum circuit. So basically, like what I'm telling you is that do the composition, okay, and then the result is just one single operator. So the circuit operator gives you that result. For example, you see here like that quantum operator at the end is basically the result of like applying all those like operators on the top of each other, and you're going to get one big basically operator representing the circuit. Okay, So that's one way of looking at the circuit. But remember that most of the time when people talking about quantum circuit, for them that decomposition is very important. So they would like to see that sequence of operation. So circuit operator is not very interesting, but anyhow, if you want to see what is the actual operation, that's one way of looking at it. And of course, quantum circuit operator, it contains collection of many different things. For example, look at that the last example that Nick is showing you. So we have Hadamard. Let's try to read the code, and compare it that with the diagram. So as you can see, the first one is Hadamard. It has no other argument, so it means Hadamard on the first one. Look at the diagram, exactly Hadamard on the first one. After that, look at that, we have the C naught operator. And for C naught, there is no argument. So automatically by default, first one is the control one and the second one is the target one. After that, we have the square root of poly x. So the square root of poly x is applied. There is no argument there, so it is applied on the first one. What you see here, barrier, is just for the sake of visualization. Okay, like, again, some people, they prefer to see like different segment of like a circuit operator, so that's how you can visually separate. And after that, look, after the barrier, we have root swap. So that's a root swap because it acts on two, it's a composite operator. So as you can see, it acts on like qubit number one and qubit number two. After that, look, the next one is complicated, but let's try to understand that. It's a rotation. The corresponding angle is theta. It represents poly x on the first one and poly y on the second one. So practically, it is like, using the standard formulation, it is the exponential negative I theta over 2 and then poly x poly y, the tensor product of those two. And that's what we have as the next operation. After that, we have permutation. So for the permutation, so it's a permutation. And then for the cycles, we say like, permute first one and the second one. And if you look at the diagram, that's exactly what's happening there. For example, like, let's change that. So look at here, this is a more complicated situation. So this is another permutation using different cycles. So like, that's how, we would represent that. And by the way, like, you can change any, for example, for the root swap, Nick, make it on the first and the third one. For example, just to show you like, now if you look at the swap, as you can see, the root swap is acting on the first and the third, qubit. So that's the case. So the second argument for the order, you can go with the default one, or if it's given, we would just consider that very specific order. Look at like, for example, after the permutation, we have another interesting like, quantum transformation. That's a quantum channel. That's how we would represent the effect of the noise in a deterministic way. So it's a bit flip with the probability p. And as you can see, like, one interesting feature about like, this framework, very similar to the usual Wolfram language, you can do the symbolic calculation. Okay, that's one of the many upper hands that we have compared to many, almost all other quantum platforms out there. We can safely say that this is the only platform that you can do symbolic quantum computation. So what you see here is basically sandwiching of like some cross operators representing like bit flip, and that's basically the operation. So like you see, uh, that's the representation of the bit flip in a traditional form. And then after that, after our quantum channel, we have a barrier, and then measurement on the first qubit, measurement on the second qubit. Remember, like, there are lots of details that you are not familiar with yet. We are trying to give you the big picture. So like, basically, like, that's the big picture, what's happening behind the scene for quantum operator. So this representation, we usually call it like, the shorthand representation for our circuit operator. So here we are using a collection of named operators, and then behind the scene, we do the calculation for you. For example, we automatically understand that, when you give a string edge, this is the quantum operator Hadamard. You can give it explicitly. For example, nothing is wrong if you just literally type quantum operator and then Hadamard, but you don't need to do that. Okay, so it's just like that's exactly the same thing. Like basically like we automatically wrap each of those named operators by quantum operator, and we take care of all the ordering and everything else that uh, that that should be done. So take home lesson here. So what's the take home lesson here? Whenever we think about the circuit operator, we have a collection of named operators that we can use, and each of those operators, the most important argument besides the name of that operation is the order. If you do not specify the order, we would treat it automatically. But if it's specified, we go with whatever specification is given for that order. Okay, so that's the overall, picture, overall review of like, our circuit operator. So before we move on to the next topic, any comment, any question? And by the way, like, look at here, like, these are the objects acting on your quantum system in the order from left to right. First that quantum operator, then the next one, and the next one. And look at that, each one, they can have different dimension, they can have different, like, qubits. When we use qubit with d, it means like, that's a very generic term, meaning that your quantum system, they can be in any dimension. And we say qubit, it means there are two-dimensional quantum systems. Any comment, any question before we move on to the next topic? And again, remember, I'm just giving you the big picture. There are lots of details that we will discuss, like, later in the following sessions.
Mads, it does look like there's a couple questions in that QA panel. I think if Nick is showing, you should be able to look at that in your browser.
Okay, so let's go. Why Rx and Ry are connected by Y? Very good question. So, like, for example, Nick, one con, take that R rotation operator. Yep. So that operator. So what is that operator? This is basically the exponential negative identity. So like we can do it manually if you so and yes, yeah. So in a sense, it's a very bad terminology in the literature, but like that's how people talk about that. So remember, you have an exponential term, you have two operators x and y, therefore you cannot write it down as the multiplication of two operators because they do not commute. Okay, there are like some decomposition how we can do that. So how we can communicate this idea that look, since these two do not commute, pay attention that they're exponential. Okay, like it's not the same. That exponential, like practically for some operator, it represents, it's very similar to the time evolution. It's not separable. How we would communicate that? We just put a wire between the two. Like these two examples that Nick is showing, look at here. Like here we have two separable operation, x and y, completely separable, but the next one is not separable. Okay, so that's the main reason that like we connect them by a wire. So it's just one way of reminding you that look, it's, you cannot, like that tensor product in the exponent, it doesn't mean like the tensor product of like two operators. Remember that. So let's see, Robert, how do you switch between the different output display form, like using the shorthand? So the shorthand is for Nick, type traditional forms at the end just to tell people what you are doing. Shorthand is literally
On the
like,
side, the coordinate diagram itself, it's the same, almost the
yeah,
same. It's just making the traditional form.
yeah. So there are like let's say that three different way of doing that. You can just evaluate your quantum circuit operator, and you're going to get, a circuit object. This is what we see with the summary box. Then you can look at the traditional form, using the shortcut command, shift and T. It shows you like, the traditional form. The traditional form of a circuit operator is literally the diagram, the output of like, that operator. So that's how you can switch. And if you want to see, again, see the object, like, you should, command shift and you go back to the standard form. Why it is important? Because look, the diagram is only a diagram. So a diagram, you cannot apply a diagram on a quantum state. But if you keep it as like, a circuit operator, because it's a circuit operator, it understands like, it can act on another quantum state. Or you can form, a composition. So the shortcut for the diagram is basically Command Shift T on Mac. So if you just double click, for your Nick, double click on the circuit, quantum, the circuit object or the cell, it doesn't matter, and then Command Shift T, you can see the diagram. Cassidy, there is a question by Henrik if the questions is available only to presenter or everyone in this session. So I will read all the questions. I do not know if you guys can see the question by other.
They're visible when we answer them.
Oh, okay. Okay. What else? And by the way, like, again, remember everyone, like, we are giving you the big picture here. Like, there are lots of details that, we will discuss in the following sessions. But I know, like, we just give you the basically a final interesting thing. So, like, that's why, like, kind of like, it's kind of cheating, but like, it helps you to have the bigger picture. Okay, so like, you remember we said, like, there are two motivations to have quantum circuit operator. If quantum circuit operator is only, if it's only a composition of operators, so fundamentally you could have told us, like, okay, so what's the point? Like, you're just, it's a just diagram, which is very nice, very beautiful diagram, but is there more to that? And the answer is yes. So if whenever you are doing a very complicated, calculation using the quantum circuit diagram, we have different methods for calculation that can help you to do that calculation faster. So I'm just going to give you the taste, just one taste of that. Okay. Just to give you an idea, like, why the circuit, is a good object. For each circuit operator, there is a tensor network representing, like, basically that that particular the operation. And how you can see that, just ask for the property, tensor network. And this tensor network behind the scene, for example, look at here, we start with the initial, and then, like, the each vertex represents, a very particular, gate, and you go from one and then to the other one. Okay. And by the way, each label on the vertex, that's the label of the operators that we have. That's the label of each gate that we have in the circuit. So we can also extract each one of those in case if somebody is interested to do that. The way that we do the computation, we do not always do, actually by default, we do not do the conventional Schrodinger approach that you're familiar with, meaning that just multiply a bunch of matrices and, like, that this is what we call as a Schrodinger approach, and then on the quantum state and get a final result. What we do behind the scene is a fancy, using, Nick's terminology, tensor juggling, tensor indexes juggling, and this is faster than the usual, Schrodinger approach. So that's why, like, whenever you have a complicated, computation, a very good practice is to write it as a circuit operator, because the computation will be faster. Of course, because of the visualization, circuit operator also helps you a lot to have a better design when you have a composition of, different operators. Okay. So that's one reason, like, circuit operator is a good function to work with. Now, behind the scene, as you see, so what we have is a transformation of quantum state, and that transformation for us, we represent it as quantum operator. Okay, so just to give you another taste, how things are done in our framework, let's very quickly review another important object that we have in our framework, and that object is quantum operator. So the most important thing that you have to remember about the quantum operator is that you give an argument, and then the second argument, basically the first argument, you are specifying your operator, and the second one, you specify the order. And by the way, before we go into the details, Stefano, his question is that if I have a complex circuit, can I full simplify it? The answer is always yes. So all those usual operations that you can do, basically all other mathematical operation that you have in in Wolfram language, you can also apply it here. Okay, but you just need to be very specific. Full simplification, if you mean full simplification and getting another circuit, that's tricky, but you can do the full simplification on, for example, the corresponding matrix or the overall operator representing your system. For example, look, Nick is showing you two examples here, maybe on the traditional form. Yeah. So you see here, we just apply, the full simplify, on our circuit.
We apply it to the final state.
Yeah.
We just simplifying the final state after composing all the gates on the blank register.
Makes sense. I know, again, there are lots of details, we will discuss about all those details. I wonder if you guys noticed that, for example, a very interesting, equivalency testing that Nick did, Nick, if you scroll up, that's a very useful opera. You see here, literally, that the type of a sort of, Ising type of interaction. We just created that manually. Look at that. There are a couple of interesting operation happening here. We are applying exponential on a quantum operator. So behind the scene, we understand this sort of arithmetics apply on quantum operator, and then you can check if these two are equivalent, if these two are the same, and the answer is, of course, yes. Anyhow, so let's go to the quantum operator, but feel free, as we discussed, please, type your questions, and we are going to answer each of those questions. So let's go to the quantum operator. So the first argument, you specify your operator, and then the second argument, you are specifying the order. For example, here, I don't know, X, Y, Z, whatever you want to do. Now, this time, Nick is saying explicitly the order is 2, meaning act Pauli X operator on the second quantum system. Because Pauli X acts only on qubits, two-dimensional quantum system, automatically we understand that, look, this is a 2 by 2, basically a matrix representing that quantum operation. You can go, why I'm telling you that, because in our framework, all the operations that you do, your quantum system, they can have any dimension as far as they are finite. Okay, so you can go in any other dimension, and behind the scene, we would take care of all those dimensionalities and how things acting on different systems. For example, if you are familiar with the generalized definition of Pauli X in 3 dimension, look at here. This time your operator, the dimension is 3, because the operator Pauli X, it's 3, and then likewise you can also go to higher dimension. So it's just a generalized Pauli X in higher dimension. And of course, this generalization, we always follow the conventional definitions that we have in quantum theory. Look at that, look at the dimensionalities that we have there, it's dimension 4, and it's acting on. So the meaning of that system is that behind the scene, because you are applying a quantum system in 3D, we understand that the corresponding quantum state should be in 3D. Okay, these are the things that we do behind the scene. So After specifying basically the nature or the name of your operator, the most important argument is order. Remember, the order by default is one. If it's a complex operation is one and two and so forth. For example, look at that quantum operator swap. So that quantum operator swap, by default, it acts on two systems, so the order is one and two. Permutation, okay, so the same with the permutation. And of course, we already showed you, whenever you are not confident about the order or what's happening here, the corresponding diagram in quantum circuit, it helps you. So look at here, now you can see that, oh, okay, it's a permutation between the first one and the second one. Okay, so that's how you can basically see that. And look at here, Nick is adding swap, into that. And we can also change the order. For example, we can say that, okay, what if I change the order of swap, and what's going to happen? If you are not familiar, how order works, just, wrap it as a quantum circuit operator and look at the diagram. Now it gives you a better understanding. Okay, now I have, for example, look, the first swap, first one and the third one, then the next one, second one, and the third one, and then the next swap, it acts on the first and the fourth one. So you see, you can customize that. But if you do not specify that behind the scene, we would just set it by default. Or look at the permutation here. The permutation, the cycle is 312. So basically, here we are saying that switch the third one by the first one, and then automatically it's like a clockwise circle. So the third one goes on the top, and then the first one becomes the second one, and then the second one becomes the third one. And you can add any other fancy permutation. And whatever you do, look at here, this time, the last example. So first, what we can do, you can give your permutation, and with no order, automatically would assume that, oh, you mean the first one and the second one and the third qubits. Now what Nick is doing, Nick is specifying a very particular order. Nick is saying that, look, I have that permutation. Now let's play with the order. And then you can play with the order. I know the example that Nick is showing, maybe it's too complicated. So
I think
just
the
let's
diagram a little bit broken.
yeah.
But I don't know.
So you see here, look at the order. So this is the same cycle, but this time you're saying that, look, do it on the 2, 3, and 1, the corresponding cycle of 3, 1, and 2. Again, if you are not confident, diagram always helps you. And if you feel you have a very complicated, quantum operator, and if the diagram does not make sense to you, just send us an email, quantum@wolfram.com, because to the best of our knowledge, all of the operations and the corresponding diagrams are represented correctly. But maybe there is a very fancy operation that you have, and you are not happy with the diagram, or maybe there is a better representation for that. Please let us know. We would be more than happy to include that. Let's see, Nick, scroll down. Let's see what other information. So you already have shown all those examples. Let's comment those, yeah, that the one next to that, that's a very good example. Now, whatever makes your life easy, look at those three different ways of constructing a composite operators. Either you can act Pauli X on the first, Pauli X on the second one, or you can define it as a quantum tensor product, which is basically what we all learn at in our quantum courses. Or in our framework, the easiest way is just saying that look, I have Pauli X, the order applied on the first one and on the second one. All of these three different constructs, they are the same. You can easily check that, all of these three are the same. There is no difference between them. Which way you want to construct it, I would say totally up to you. But our recommendation, focus on order, because order will make your life much easier. So if you just focus on the order, you can easily do all your construct. As you can see in the quantum tensor product, So there is one question, Douglas, how would you represent, the density matrices, that's for the quantum state. We are going to discuss quantum states very soon. Okay, uh, let's see, Nick, let's just go to the quantum state, just for the sake of representation, because that was just a question. We never discussed quantum state. So remember, for quantum state, there are two ways of representing a quantum state. If it's pure, go with a vector, so just the amplitude, basically your state vector. That's one way of representing that. And then if it is, a mix, the input should be a matrix. Okay. uh how we can see the corresponding, density matrix? So just ask for the density matrix. Maybe if you show the matrix form, so that's a density matrix. Now, if you want to see it, Nick showed in a traditional form, that those Brownian kits, on directly on the quantum state. So as usual, this is basically what Nick did here is literally the same way that we do it for operators and the circuits. Just ask for the traditional form, or ask for uh, the density matrix and the corresponding matrix form. So for the quantum states, remember, there are two ways. For the pure, go with the state vector. For more than that, go with the matrix. Look at the matrix example. I wonder if you guys notice in the summary box, it says the type, basically your quantum state is unknown state. Why it is unknown state? Because we do not know if it is, semi-definite, and because of that, semi-definite positive, because that's a very important constraint for density matrices. But in our framework, you can go beyond the usual, definition for density matrices. Basically, you can release that, constraint. Those of you who are familiar with the ZX, formulations, ZX formalism, ZX calculus, they're what we call as a quantum, states, it can, you can release lots of constraints that we have on the top of your density matrix. Let me just comment on one thing, maybe those of you who are familiar with quantum, look at that quantum state and the corresponding formula. What you see there, whenever you ask for a formula, because formula, it's what is the state vector? What we do, we understand, we would, that's how we would interpret it. We would say that, if you mean something that is not pure, and if you ask for the formula, we just go to a higher dimension, because whenever you have a mixed state or an unknown state in lower dimension, you can basically, in some way, you can purify that in higher dimension, and that's how we would represent, that formula. So that's why, what we are doing here is in two dimension, but when you ask only for the formula, you can, we go into one higher dimension. uh it's the usual purify, unpurify. We will discuss about it, next time. I know, right now we are giving you, lots of information, but our goal was like this, just give you the big picture. And now what we are going to do next time, in the course of 1 week, we are going to focus on each of these objects in more detail, and we are going to discuss about all those details, how we can do, different design, different operation, how we can, basically do partial transpose, how we can do, I don't know, realignment, all those fancy operations that we can do with the quantum state, or operations. We are going to explain, in the course of 1 week, how you can do each one of them. So I think that's a very good point to wrap up our session. Any particular question, comment? Again, sorry about that initial issue with, it was my internet connection. I guess, Nick, you have a better laptop than me, so my laptop, he couldn't handle, broadcasting live and, cloud connection simultaneously.
Did Matt, did you want to run any of the poll questions?
We can do it next time, because, let's do it next time. So let's do it, we are gonna basically making sure, you're gonna engaged and you're listening and you have a good understanding. So let's do it next time. Any comment, any question? Like, so let's, Nick, scroll up at the very top. Let's one more time, like, remember, like, it's a packlet. So, like, just like, these are different ways of, installing the packlet. Always go with the development version, because, like, if any issue, we would just take care of that, like, immediately. For example, you notice, like, the wiring for the permutation, they were not, very, nice. That's one thing that we just, me and Nick, it may take 10 minutes or less. So, like, if you next time, if you upload your packlet one more time, that minor issue that you saw in fancy permutation, like, it will be resolved. By the way, for the same reason, whenever you are doing any computation, remember, install the latest version, because if there was any issue in the previous versions, I don't know, like, maybe there is an issue with the diagram or etc., we just take care of that. But, like, if you want to see, like, the correction, you just need to install the latest one. So a healthy practice, whenever you are working with our framework, make sure that you install the latest version from the development site before doing any computation. Let's see, let's look at the questions. So Miguel, like, regarding, quantum circuits from Wolfram to Python, we are going to discuss, yes, you can do that. You can ask for the Qiskit. You can, like, do all those things, like, it's, you can easily go to
I
Python.
can preview it a little bit.
Yeah.
If you want.
Let's just show one example. Yeah. For example, that's the Foley. You can ask for the Qiskit. And by the way, the moment that you say, Python, remember, like, your external evaluate, etc., you just need to set them up. So this is the Qiskit circuit, and, like, it's not only
This
that,
will
like,
work the same way as our circuit. It just goes for the Python environment,
yeah.
runs a simulation there,
Hmm.
and returns it back. For example, if you want to apply it to an empty register, it will go through the Qiskit simulation.
Yeah. And by the way, remember that, like, Qiskit, like, what we do here, all the simulations that you see, it's, I shouldn't call them simulation. It's because it's not a simulation, because Wolfram Mathematica understands, like, probability and statistics. Many of the things that we do here, they are exact. Okay. So, like, that's a very fundamental difference between, like, the ours and, other, like, simulators out there for us, because again, like, Mathematica understands probability and statistics. All the calculations are practically exact. Step-by-step books, there is another question: are there any good step-by-step book guideline? I would refer you to our documentation. Okay, so, like, the documentation that we have, that's the best place, uh, that it provides all the details how you can get it done. But if if a better, like, approach for step by step is needed, let us know, like, in our future Wolfram U events, we can provide that step by step. Register state, it means, like, in whatever. So there is another question about register state. Register state with no argument, just saying register state, it means all the quantum system that are in the ground state 0. Okay, so, like, that's, but, like, you can go for, because, like, we also have register index state. Okay, you can have a third argument, like, and then show the formula, show the, yeah, the traditional form, like, they would, yeah, 0, 1, yeah, 2, and you see here, like, the usual order for register state. But if you just say register state, means usually, like, all of them are in 0 state. Any reference, as I said, our documentation very similar to, like, the documentation that we have, in Wolfram Mathematica. We did our best to write it in a way that is self-consistent and contains everything that you need. Besides that, like, there are lots of good textbook on quantum computation and quantum computing. So uh, any textbook, different, people, different, backgrounds, different textbooks. So pick any textbook and try to implement it in our framework. Okay, I think, we are good. Let's call it a day. So thanks everyone. We will meet, tomorrow. And please let us know any question, any comment, any concern. Like, let's make sure that, it is like, sort of interactive, sessions. And, based on your questions, we will be running our study group. So quantum at wolfram.com, and also that link that Cassidy shared, like, that community post. Let us know what you think, and, we can basically answer your questions. Thanks everyone. See you tomorrow.